This is part 4 in our series of lectures on section 3.1, and in this lecture we're going to write down some general results involving relations, and we'll include some of the proofs of those results. So we state the results in this theorem. We start with four sets A through D. We have a relation R from A to B, a relation S from B to C, and a relation T from C to D. Then the following three results are true. The first one is referred to as identity for composition. It says that if you take the composition of R with the identity on B, the identity relation on B, that's the same as R, and the composition of the identity on A with R is equal to R. So you notice that that makes sense because R is a relation from A to B and IB is a relation from B to B. So this is a relation from A to B, as is R. This one is a relation from A to A. This is a relation from A to B. So the composition is a relation from A to B, again, as is R. So at least it makes sense. And this is the result that I alluded to when I first introduced the identity operator, the identity relation. I told you that it behaves sort of like the number 1 does with respect to multiplication. It has the property that when you compose a relation with the identity, you get back exactly what you started with on either side. So that's why we refer to it as the identity for composition. The second result we're going to prove is referred to as associativity. It says that if you compose these three relations, it doesn't matter if you group these two together or these two together when you're doing the composition. And finally, this very, very important result, and you'll revisit this result in a lot of different disguises as you do more advanced courses. It says that if you compose R with S and then take the inverse, that's the same thing as first inverting S and composing it with the inverse of R. Let's just check that these are relations from the same set to the same set. R composed with S is a relation from A to C, so the inverse is a relation from C to A. This one is a relation from C to B. This is a relation from B to A, so the composition is again a relation from C to A. So at least it makes sense. You'll notice from a mechanical point of view, it's saying that if you want to distribute an inverse over a composition, you should take the compositions of the inverses, but in the reverse order. Okay, here is the first result that we are talking about proving, and I'm only going to do this one here, and I'm going to leave the other one as an exercise. Now, how would you prove the first one? Well, remember, relations are sets. They are subsets of certain Cartesian products. So this is a set, this is a set. And how do you prove two sets are equal? You have to prove that this is a subset of this, and this is a subset of this. And in order to deal with this left-hand side, that's a composition of two relations, and so you have to make use of the working definition of composition that we talked about in an earlier video. And you also have to make use of the working definition of the identity relation. Remember, I warned you in an earlier video that it's okay to do calculations intuitively with an intuitive understanding of what a composition is, but in order to write a formal proof of a theorem such as this one, you really need to make use of working definitions of compositions and identity relation. So why don't you put your video on pause and see if you can write down the proof of the equality of these two relations. And when you come back, you can compare your answer to mine. Okay, so as I indicate here, we will prove that the composition of R with IB is equal to R, and leave the proof of the other one as an exercise. So I'm first going to show that this one is a subset of this one. So this is a relation, it's a certain subset of A cross B. So we begin by saying, let xy be an A cross B. Suppose that xy lies in the left-hand side. Now I have to use the working definition of composition. What does it mean to say that xy lies in the composition? It means that there exists this linking z, this z in B, such that xz lies in R and zy lies in IB. That's the working definition of composition. Now what does it mean to say that something lies in IB? It means both components are the same. So I say, since zy is in IB, it follows that z is equal to y. Well, z is equal to y, and we've said that xz is in R, so that means xy is in R. So I started off by taking an xy in IB, in R composed with IB, and I proved that xy, is an element of R, and therefore I've proven this inclusion here. Now we have to prove the converse, the opposite inclusion, that R is a subset of this composition. So again, we begin by giving ourselves an element of the Cartesian product, and we assume that that element lies in the left-hand side, and I have to prove that it lies in this composition. Well, in order to lie in a certain composition, we have to prove the existence of a certain linking element in B. And in order to prove the existence of that linking element, we have to figure out how to choose it. And I looked ahead and I realized that the correct way to choose it is to choose z equal to y. So let's see why that works. If z is equal to y, we know that z is an element of B, right? Because y is an element of B. We know that xz is in R because we know xy is in R. And we know that zy is in IB because zy is equal to yy. And the definition of IB is that both components are the same. Well, these three things together tell us that xy is an element of IB, or R composed with IB. That's the working definition of an element of R composed with IB. So I started off by taking an xy in R. I proved that it was in this composition, and therefore I've shown this. So together, 1 and 2 show that we have the equality of those two sets. Now let's turn to the proof of the associative law. And once again, this is a relation, this is a relation. That means they're both sets. And so I have to prove that this is a subset of this, and this is a subset of this. I'm only going to do one of those. I'm only going to prove that this is a subset of this, and I'm going to leave the other one as an exercise for you to do. But once again, in order to do it, you're going to have to make very strong use of the working definition of composition. Otherwise, you won't be able to do it. So put your video on pause and see if you can come up with the proof that this is a subset of this. When you come back, we can compare our solutions. Well, here's my proof. I'm going to prove this inclusion here. So now remember that this is a relation from A to B, B to C, C to D. So this taken together is a relation from A to D. So I begin by giving myself an XW in A cross D, and I assume then that it lies in the left-hand side. And I have to prove ultimately that it lies there. Now what does it mean to say that it's in the composition of, it's the composition of two things, this one and this one. So in order for XW to lie in this composition, there has to exist a linking Z in C such that XZ is in the first factor and ZW is in the second factor T. Well, now I'm going to write down the working definition of this statement here. There has to be a linking term in B, and so that means, since this happens, there has to exist a y in B such that xy is in R and yz is in S. That's the formal definition of this statement here. Well, I have to relate all of this to something in this composition here. So, since yz is an element of S and zw is an element of T, as we've just finished saying, and this linking term z is in C, it follows by definition that yw lies in S composed with T. So now we've got a y is in B, we have xy is in R, and from here we have yw is in here, and so by definition xw lies in this composition here. It's strictly a matter of following the working definitions of composition. So you see, I began by taking an xw in this composition, and I proved that it was in this composition, and that means that this is a subset of this. Now let's turn to this result here, and I'm only, once again, these are both relations, and once again I'm only going to prove one inclusion. I'm going to prove that this is a subset of this. In order to do that, you have to make use of working definition of inverse and of composition. So put your video on pause and try to write up a proof that this is a subset of this. Well, here's my proof. I'm going to prove this inclusion here. I'm leaving the reverse inclusion as an exercise. So recall that this is a relation from C to A, and so I begin the proof by giving myself a generic element in C cross A, and then I suppose that it lies in here. Suppose that Zx lies in the inverse of R composed with S. Now what's the definition of that? Well, the first thing you should see is the inverse sign, not the composition. To say that this lies in the inverse is to say that if you reverse the arrow, reverse the order in the ordered pair, that lies in R composed with S. Now what's the definition of this statement? Definition of that composition is that there exists a y in B such that xy is in R and yz is in S. Now let's rewrite these as inverse statements by reversing the order. So by definition of inverses, that means this one here means that zy is in S inverse, and this one means yx is in R inverse. So you see this linking y here, which is in B. Since y is in B, then by definition of composition, it follows that z comma x lies in R inverse composed with, lies in S inverse composed with R inverse, which is what we wrote here. So that's what we wanted to prove. We started off by giving ourselves zx in the left-hand side, and we proved here that zx is in the right-hand side. So that proves that this is a subset of this.